Hello, I welcome you all to this another interesting screencast. The problem reads, when x is equal to 10 feet, the crate has a speed of 20 feet per second, which is increasing at 6 feet per second squared. Determine the direction of the crate's velocity and the magnitude of the crate's acceleration at this instant. This problem is coming from the Engineering Mechanics Dynamics textbook, 14th edition by R.C. Hibbeler. So we have a crate which has a speed of 20 feet per second, and this speed is increasing at 6 feet per second squared. So what can we notice here? This value is constant, which is the acceleration, right? This is constant. Okay, it's constant. Okay, this is what we've been told. This speed is increasing at this rate, so it keeps on increasing at this rate, so it means the acceleration is what? Constant. So when it is constant, again, what does it remind you of? When acceleration is constant, we can use these equations. Okay, you can use these equations, right? It's up to you to pick which one you're supposed to is appropriate for your problem. Right, so you can use these equations to sort out your problem. So here we're being asked to find the velocity, the direction of the velocity. Velocity is already given, but the one direction at that very point, at that instant, which is at x equal to 10 feet, which is this very point. Okay, so we want this direction here. Okay, this direction here. What is this slope at this point? The slope. Okay, so we need to calculate that, and then we need to find the magnitude of the crate's acceleration. And what are we missing here? The what? Rho. We don't have rho. Alright, so we need to calculate the rho from the equation for the radius for and the curvature. Alright, first things first. So we have let's work out. So we do have velocity, and our velocity, which is just st, is equal to ds dt. In our case, it has been given as 20 meters per second. And then our acceleration, of course, velocity, if we are to express velocity as a vector, then this would be equal to v, then u t in that manner, like so, which is just a unit vector along the tangential direction, which is this one there. Okay, so we have that direction, then we have that direction. This is n, this is t. Okay, all right, and then we have acceleration. If we express acceleration as a vector, then this is equal to at ut, which is a unit vector, then plus an is this centripetal acceleration, then by un, unit vector along that particular direction. Okay, and our at is just going to be equal to, our at is equal to, we already know it, since the acceleration is uniform, this is just going to be equal to 6, it is 6 meters per second squared. And then an will be equal to v squared divided by rho. Okay, where v here we already know at this point v is equal to v is equal to 20, right? It is equal to 20, at that instant. It's 20 meters per second. Then for rho, we need to calculate it. This is equal to 1 plus y prime squared, everything to the power 3 over 2, then divided by y double prime. Again, this is a standard equation which you can check out in your textbook on how to derive it. Okay, so equation for the radius for any curve, given that you know the function that is defining that particular curve, right, which is y. So we have our y in our case there, which is equal to 1 divided by 24x squared. Therefore, y prime for this, which is the first derivative. So y prime simply means dy dx. Okay, this is what we mean by y prime. And then y double prime, that simply means dy, this is a double derivative. Okay, this is what it means. Okay, so you work out the derivative twice. That's y double prime. So y prime there, then this just becomes a 2 goes this side, then this we divided 2 into 24, it becomes 1 divided by 12x. Alright, and then y double prime, this is just going to be equal to just 1 divided by 12, like so. Okay, and therefore our rho, if you are to plug in this value, just becomes 1 plus 1 divided by 12x squared, okay, to the power 3 over 2 divided by 1 over 12. So we are evaluating this at x equal to 10. Okay, our x is equal to 10 feet. So plug it in. So we'll say rho at 10 equal to, at rho at x equal to 10. So this becomes 1 plus 1 divided by 12 by 10. So this, the whole lot of this squared. Okay, and then the whole lot of this, the 3 over 2. It's not looking too good. Let me write it properly. Let's go to the other space. Things are getting a little bit messed up here. Okay, so there we go. So we are saying we do have our rho there. We said rho, evaluating it at x equal to 10. So this becomes equal to 1 plus 1 divided by 12 times 10. Okay, and then this everything to the power 2, and then this everything to the power 3 over 2, and then divided by 1 over 4. So this is our rho. So now I want to plug in this directly into there. So let's use this equation once more again. Our an is equal to v squared divided by rho, and our v is equal to 20 meters per second. This is not seconds, sorry. This is not seconds, this is 20 feet. Sorry, this is 20 feet per second. This is what I wanted to get worried because I was using feet at some point, sorry. Okay, this is feet, right? So now let's plug in these values. We plug this in here, and then we plug this here. Okay, so we grab our calculator and then do that. Then we should be able to find a value which I don't know yet. Let's work it out. I'll start with the bottom. So I'll say 1 divided by 12 by 10. Okay. To the power 3 divided by 2, 1 divided by 12. Okay, and 20 squared divided by answer. So here I'm finding a 15.11, that's not meters, this is feet per second squared. Let me repeat this. It's a 10 divided by 12. Okay, then squared, then plus 1, then to the power 3 divided by 2 divided by 1 divided by 12. Okay, and 20 squared divided by answer. Right, so there we are. So we have this one. We also found 80, which was just constant throughout, and it is 6, not meters, Sorry again about that. When we are used to SI units, sometimes, okay, like so. Okay, so this is 6 feet per second square. So now we need to find the magnitude, and the magnitude is just equal to square root of 80 squared plus an squared, and therefore our A is just going to be equal to, when we plug those values in there, so we'll have 15.11 squared plus 6 squared, square root of that, so we have a 16.26 feet per second squared. So we are done with the first case. We need to find direction. The direction, we can find it using the slope of this particular curvature, and it's been governed by this y. Okay, so we know that y is equal to 1 divided by 24 squared x squared, and y prime, which defines the curvature, which defines the slope. Okay, first derivative, which defines the slope, is equal to 1 divided by 12x, and then y prime at x equal to 10 feet is just going to be equal to a 10 divided by, or if you'd want to leave it the way it is, 1 divided by 12 times 10. So 1 divided by 12 times 10, this just becomes, we'll leave it like this, as a 10 divided by 12. So let's now find this angle in degrees. So say theta is just going to be equal to tan inverse of 10 divided by 12, and therefore our theta is just going to be equal to, let's work it out. So tan inverse, where is the function for tan inverse? Okay, so tan inverse of 10 divided by 12. Alright, so this gives us a 39.81 degrees. Alright, so our velocity is equal to 20 meters per second, and we have the slope. We do have the slope of, how do I indicate it? Like so. Okay, we do have the slope like so of theta, and that theta is equal to 39.81 degrees. I think we are done with our problem. We just need to outline the solution. So we have the acceleration here. Okay, this is our acceleration. All right, and then we have velocity there, which was already given with this direction. Okay, and then let me just indicate also, let's say this is our tangential. Okay, and then this one is our normal. Okay, which produces the centripetal acceleration like so. And then let's say we have the resultant of our acceleration. Which one was bigger? The normal was bigger in our case. So let's say our result maybe is somewhere there. Okay, closer to the normal. All right. Okay. So let's say this is the resultant. This is an, and then this is a t. Okay, and then we do have the slope, which we've already shown. We do have the slope. This is the slope, which we just calculated, right? Okay, this is our slope at that particular point. Okay, right. So I hope this particular video was helpful. Maybe let me show this slope here. It's no problem. You can show it anywhere. Okay, so let's say this is our slope. Right. I think this is about it. I hope this video was helpful. I hope it was helpful, and if it was, give me a thumbs up. Like my video, continue subscribing and liking my channel. Bye bye, and I'll see you in my next screencast.